Uranium. Make a video about uranium. Uranium. Maybe he just cannot make a video about uranium.
We'll see about that.
Oh, hi, Max. I think they wanted you to film something about uranium. Here's your uranium.
Oh, that's nice. Thank you. Oh.
Hello everyone. I guess you have figured that this video is going to be about such a metal as uranium. However, let me give a small warning in order to calm you down.
We're currently in the uranium lab. We're certified to work with radioactive materials such as uranium, so there will be no official problem. Welcome.
And of course, don't try to repeat that experiments at home, even if you have 2 pounds of uranium in your garage. I think now we have settled everything and can move on to considering properties of the most dangerous metal on Earth, uranium. Uranium belongs to the actinide series in the periodic table, that is to radioactive elements, and its atomic number is 92. Uranium is 40 times more abundant in Earth's crust than silver. It is so abundant because it forms upon rapid neutron capture inside spinning supernovas. That is why uranium was discovered quite early in Germany in 18th century. Its discoverer, Martin Henry Klaproth, named it after a newly discovered planet of the solar system, after Uranus. In nature, uranium is often found in such minerals as uraninite and autunite. This metal often has several oxidation states in those minerals. Thanks to the beautiful yellow color of such minerals, glass blowers added them to glass. As a result, minerals would give such a glass a beautiful greenish color. It's a pity that back then craftsmen didn't know about the toxicity of uranium compounds. Nevertheless, pure metallic uranium can be obtained from uranium ore via reduction by calcium, and it looks very ordinary, since mostly uranium naturally occurs in the form of uranium-238 isotope with a half-life of about 4 billion years. Depleted uranium is most frequently used for chemical researches, in order to reduce scientists' exposure to its radiation. Pure uranium obtained from its ore looks quite dark, as its surface oxidizes pretty fast because of the high chemical activeness of this metal. That is why it is often stored in argon, and also all experiments with uranium are conducted in argon atmosphere. Usually, to conduct experiments, a piece of uranium-238 is ripped to such small threads on a lattice in laboratory. It is noteworthy that these threads in the test tube already emit beta and gamma radiation. Gamma emission alone is 50 times the normal level. This emission is caused by the decay products of uranium, which breaks down even further to beta and gamma particles. The walls of the test tube confine the alpha rays. Because of its high chemical activeness, uranium shreds burn well in the air. For the first time on YouTube, you can observe how uranium burns and turns into its oxides. However, to conduct experiments, uranium is not just burned. Uranium shreds are mixed with iodine crystals, and the chemicals are let to sit for a few days, sometimes with a solvent, in order for them to react. The reaction produces uranium triiodide of such violet color. The reaction can also produce uranium tetraiodide, depending on the proportions of agents. These metals compounds with +3 or +4 oxidation states are most frequently used as raw materials to create uranium complexes, and are also used as catalysts because with such an oxidation state, uranium is the most chemically reactive, because of having a lot of electrons in the f orbitals. It is noteworthy how quickly the color of uranium compounds changes depending on the oxidation state. For instance, it can be seen when comparing uranium triiodide and uranium tetraiodide. It is also worth of noting, when tetrachloride is used instead of uranium tetraiodide, the color will also change drastically, from orange to green. By the way, uranium tetrachloride used to be used in early electromagnetic isotope separation uranium enrichment, but soon this method proved to be inefficient and was substituted by other methods. Nevertheless, uranium compounds with +4 oxidation state are quite stable. That is why they are used most frequently. For instance, enriched uranium dioxide is used as nuclear fuel for atomic reactors. However, the oxidation state of uranium can be increased to +6 oxidation state. For instance, dry uranyl nitrate is a beach powder. In this form, it is most frequently used for experiments. When exposed to air, this compound absorbs water very well, and it turns into beautiful hexahydride crystals, which glows in ultraviolet light very well. Uranyl nitrate is also formed when pieces of uranium react with nitric acid. Besides, at this particular moment, the shiny surface of the element can be seen very well. In fact, many compounds of 6-valent uranium have fluorescent properties in ultraviolet light. That is the very reason why they are added to the so-called uranium glass, which beautifully glitters in the sun with bright green color. Whereas in the dark, when an ultraviolet flashlight is pointed at it, it looks even more stunning. Because of its fluorescent properties, uranium is most frequently depicted as glowing with green in most cartoons and films. Although in reality, uranium fuel and uranium itself are usually of dark colors and don't attract much attention. Besides, it's worthy to remembering that many uranium compounds are very toxic, needless to say are also very radioactive. There are also uranium compounds with +5 oxidation state. However, only in 2006 stable uranium compounds with +5 oxidation state were obtained that didn't break down at room temperatures. It was achieved as a result of stabilization of uranyl ion with the help of organic coordination ligands. And if you think that scientists were doing useless things, I hasten to question that statement. Nowadays, because of the large amount of processed nuclear fuel, there is always a risk of water and soil contamination with well-soluble 6-valent uranium compounds. However, if they are converted to +4-valent uranium compounds that do not dissolve in water, the risk of water contamination decreases by a few times, because 4-valent uranium compounds will just sink to the bottom and can later be easily collected. Also, 5-valent uranium is often stabilized by iron ions, for instance in such an iron ore as magnetite. That is why now scientists are seeking to use it for a more efficient nuclear fuel recycling. And now, let us recall to the title of this video and answer the question why uranium is so dangerous. It's so because this is the very metal that the little boy bomb dropped on Hiroshima in 1945 was made of. This bomb was designed using gun methods. 2 parts of enriched uranium in subcritical state were shot in each other. After being contact, the mass of uranium would reach a critical point, and this would trigger a chain reaction when uranium cores would start dividing under the influence of an enormous amount of neutrons which refracted off the temper made from tungsten carbide. As a result, the nuclear explosion killed about 2,000 people, becoming the first use of atomic weapon in history. Besides, in a nuclear reactor, uranium-238 can be turned into plutonium-239 by irradiation with low neutrons. It is known that plutonium-239 is fitting for making implosion-type atomic bombs, because its critical mass is smaller. As, if that was not enough, uranium is also a very toxic metal. That is why, because of these dangerous properties, it can be called the most dangerous metal. It is also worthy of note that naturally occurring uranium mostly consists of isotope uranium-238, which cannot divide spontaneously and is not suitable to be used for making nuclear weapons. Only less than 1% of uranium, or more precise uranium-235, can run self-sustaining nuclear chain reaction and can be used to make atomic bombs. To make that bad things, the concentration of isotope 235 is increased to 85%, whereas only 3% of uranium-235 is enough to make nuclear fuel for power station. Usually enriching is done by centrifugation of gaseous uranium hexafluoride in special machines. During this process, a lot of needless uranium-288 is released and concentrated. That is how depleted uranium is obtained. Its radioactivity is much smaller than that of enriched fuel. As a result of the Cold War, there has been produced too much depleted uranium that people don't know what to do with it. Thanks to its high density, depleted uranium is used as aircraft loads for balance, as tank armor, and even as missile cores. However, because of being highly active, uranium armor can ignite, and that is why it can be risky to use. It's also noteworthy that because of the very long half-life of uranium, it is still a source of warmth of Earth. To make a conclusion, we can say that uranium is the most dangerous metal on Earth because it's very toxic and people have made one of the most destructive weapons from it. One step in the wrong direction can lead to disastrous consequences. Chernobyl nuclear disaster is a testimony to that. Humans are yet to find an efficient way of recycling uranium, with a little impact on nature as possible, and also to decrease the risk of nuclear disasters and environmental contamination. If you like this video, please give a thumbs up, and also, if you have access to some radiochemistry laboratories and you can help me in the continuation of production videos about actinide, please contact me via my email. If you would like to support the continuous production of science videos like this one, please support channel on Patreon, link in the video description.